Hello everybody, let's try to solve this simple distributed load problem and go through some of the things that might be tricky when you're first trying to do these problems on your own. So the question goes, replace the loading by an equivalent resultant force and specify its location on the beam measured from point B. So I separated this into two parts, part A and part B, and the part A is red. So replace by equivalent resultant force. What does that mean? It means we have to take these distributed loads, which are in pounds per foot, and separate each shape into a resultant force, which is a point load, getting rid of the foot. So how do we do that? Well, first we need to identify what shapes we have in the distributed load. So we have a triangular shape here. We have another triangular shape at the top here, which is a bit harder to see, but the height of this is the difference between the 800 and the 500. And then lastly, we have a rectangular distribution here. Next, we have to identify where the centroid of these distributed loads are. So we have one here, and one here. But how did I know this? How did I know that these were here? Well, we know that for the centroid of a triangular prism, or a triangular shape, we have from this end to this end, the distance will be 2/3 of x. So in this case, we have 2/3 of 12, which is going to give us 8 feet. And we can do it similarly for this triangle up here as well. We will have, let me draw another line, 2/3 of the span, which is 9 in this case, which will give us 6 feet. And then we have the rectangular shape, which is half of its span. So we have 1/2 instead. So 1/2 of 9 is equal to 4.5 feet. So now it wants the resultant forces of each one. So that means we're going to take a line from these centers. Okay. And we need to determine what this value will be. So for, let's say F1, F1 will be the area of this distributed shape. So we have, for a triangle, it's 1/2. The peak of it is 800 pounds per foot. And we have the span it covers, which is 12 feet. And you can see the feet cancel out. So that gives us a number of 4,800 pounds. And similarly, we can do the same for, let's say, F2. F2 will be the same formula, 1/2. It's going to be 800 minus 500. And the span it covers. And that will give you 1,350 pounds. And then F3 is a little different because you don't need the half coefficient because it's a rectangular shape. And the height of it is 500. Taking the span once again, we have 4,500 pounds. So what's our resultant? This means that our resultant force will be the summation of all three, which adds up to 10,650 pounds. But what's the sign of this resultant force? Well, if we consider that upwards is positive in our convention for F, then that will mean that this should be negative because this is going down. Now let me clean this up and we'll get solving to part B. Alright, so now I have everything set up from the previous part of the question. Now it wants us to specify the location of FR on the beam measured from point B. So I drew up this little sketch here to just have a representation of what it means. So it's looking for where this resultant force is going to end up with respect to location B. But how are we going to do that with only forces? Because we converted pounds per feet into pounds. Well, now we actually need to use our equilibrium equations to try and figure this out. Well, remember we have summation of forces is equal to 0. But we also have the summation of moment is equal to 0. So what does that translate into? We have moment is equal to force times distance. But in our case, if we took the moment at B, it would be equal to the force of the resultant times distance x. Why? Because we know this is the summation of all forces. So distance x from that point B will cancel out the moment. So if we isolate in our case for x, we can actually solve this problem. So what are we looking for? We're looking for a moment at B divided by FR. So the first thing we could do is figure out what x1, x2, and x3 are. And we know, once again, moment is 4 times distance. So we need these distances from f1, f2, and f3 so that we can actually solve for the moment. So x1 is going to be 12 minus this distance. So we have the span from B. We just need to find the distance between this force to find that lever arm. So it's going to be 12 minus 8, which is equal to 4 feet. x2, similarly, we're going to take the span that it covers minus 6 feet, which is what we calculated previously, and x2 is going to be 3 feet. And then x3 is going to be similar, 9 minus 4.5, which is going to give us 4.5 feet. Now we have everything we need to solve for x. So x, once again, is equal to moment at B over FR. Remember that FR is going to be negative because we chose this convention, and we know that a typical moment convention is clockwise is going to be negative, and counterclockwise is going to be positive. So let's consider F1 here. F1 is going around B in a counterclockwise direction, so we have to give it a positive sign. So we're going to consider positive F1, which is 4,800, and we have pounds multiplied by the distance x1, which is 4 feet. Pounds per foot, that's the perfect unit for a moment, so you're good there. F2, similar process, except this time it's going clockwise, so we have to give it a negative sign. We remember our numbers, 1,350 pounds times the distance 3 feet. And then similarly for x3, we are considering negative for clockwise movement, 4,500 pounds times that distance, 4.5 feet. And all of this is going to be over our FR, which was what? Negative 1,650 pounds. The pounds are going to cancel out, and it's only going to leave us with feet. So solving this, you'll be left with 0.478 feet. And that is your final answer for x. I hope this helped.